Okay, good morning students. Now already the different types of potential surface for various cases we have done. Okay, now next is we know that E dot dl, dv is equal to E dot dl last time I taught you. So in if suppose say it is potential gradient, E dot dl is equal to dv. This is what I told you. So this is a difference in the potential, and this is E and this is dl. Now suppose this is when you have to find total potential, then it will be V, but it's just dv, then it is E dot dl. Okay, now potential is a scalar quantity, E is electric field, it's a vector quantity, this is also vector quantity, but we can write this as E is equal to dv by dr or dl. Okay, here dv by dl, it is actually potential gradient. Electric field is equal to, with a negative sign, it was negative, is equal to potential gradient, negative of potential gradient. So this is the expression, this is the formula we use to calculate field from potential. If you know potential at a given surface, if you do this d by dr, you'll get E, electric field. Okay, so it's a gradient is an operator actually. dy by d or dv by dx, anything we can write, it is electric potential gradient. E is equal to dv by dx or dr, anything can be written. Now properties of equipotential surface. Now in properties, dv by dx, just now I said dv by dx, so dv by dx along equipotential surface is 0, because if it is an equipotential surface, there is no change in potential with respect to position. Hence, E along equipotential surface is 0 and electric field is perpendicular to the surface. Now, equipotential surface do not cross or intersect each other, because why they do not cross each other? Suppose you have to, this is your one surface, this is your another. This is equipotential surface 1, this is equipotential surface 2. Now, you know that electric field is perpendicular to equipotential surface. If for this surface, if I have to draw normal, this will be perpendicular, electric field due to surface 1. And for this surface, if I have to draw normal, this surface 2, then it will be perpendicular, will be in this direction, electric field 2. They both are in different direction. At same point, you cannot have two different directions of electric field. There has to be only one. So this is not possible. Two equipotential surfaces cannot intersect each other. Okay. Now next topic is electrostatic potential energy. Now we spoke about potential. Now let's talk about electrostatic potential energy. A little bit we have already done. Now it is the total amount of work done by external agency in bringing them from infinity to present arrangement in the system. So if you have two charges, okay, so the total amount of work done in bringing these two charges from infinity to this location is that will be the potential energy. Now suppose you have an empty space. This is charge q1 and this is charge q2. They both are at infinity. Now there won't be any amount of work done in bringing this from infinity to here, because there is no electrostatic force to repel or attract. So we can bring it without doing any work. Now when we are bringing this q2 here, already q1 is present, so there will be electrostatic field around it. Okay, and because of the field there will be some force acting on it, repulsive or attractive. So now when we are bringing it here, okay, without any acceleration, if you have to bring it here, then we have to do some amount of work, and that amount of work done now will be the potential energy of the system. Okay, now because it is potential energy, its unit will be joules. And so see, for two charge system, if you have two charge, one is here, another you're bringing from infinity to here, you're bringing the position vector of charge 1 is r1, position vector of charge 2 is r2, and the displacement vector between them is r12. Now when it is here, there is no other charge. First charge you're bringing, there was no other charge, so no problem. But when you're bringing another charge, at this point you're bringing, so there is already some potential, electric field is present, because of it some potential is present. So potential here at point 2, because of charge 1, v21 is kq1 by r12. Okay, now if that is potential, then work done is just potential into charge. So this potential at this point into the charge q2, if you do, you'll get work done in bringing it from infinity to this point. Okay, now what is potential? v21 is, so substitute this value, you'll get potential energy is equal to w0 k q1 q2 by r. Okay, because potential is equal, work done, potential energy is potential into Q. So remember, electrostatic force is K Q1 Q2 by R square. Electric field is K Q by R square. Potential is K Q by R, and potential energy is K Q1 Q2 by R. Okay, these four formulas remember. Okay, now next one unit is joule. Now another unit, you see this formula, potential into charge. So this unit for potential is volts, and for charge it is coulomb. So volt coulomb is 1 unit, SI unit. But there are some smaller units also which we will use, which we will require. So that is volt, and instead of Q, if we put E, charge of electron, E, symbol E, then it is electron volts. Okay, and electron volts mein E is the charge of the electron. So when you substitute charge of electron, 1.6 into 10 to the power minus 19, and this volt is 1 volt, then you will multiply these two, you will get 1.6 into 10 to the power minus 19 joule. So 1 electron volt is 1.6 into 10 to the power minus 19 joules. Okay, this is SI unit. This is a smaller unit, not SI, but very useful. You are going to use it later in other chapters. Okay, now come here. This was for two particle system, but when you have a system of endpoint charges, okay, so system of endpoint charges, so there is first W1 is the amount of work done in bringing first charge. So when you're bringing first charge, there is no other charge, no work done. Now when you're bringing second charge, already first charge was there, so K Q1 Q2 by R12. Now when you're bringing third charge, two first and second charges are already there. So when you're bringing third charge, for third charge it will be K Q1 Q3 by R13, K Q2 Q3 by R23. Okay, same way when you're bringing fourth charge, so three charges are already there, so 3 terms will come. Like in second charge 1 term comes, in third charge 2 terms come, so in fourth charge 3 terms will come, nth charge n minus 1 terms will come. No, but here, so okay, fine, that is work done in bringing nth charge. But what about the potential energy? Potential energy will be sum of all the energies. You will have to add all of them, and then we will get potential energy. Okay, so 0 plus this plus these 2 terms will come, and so on. Okay, but now see here what will happen. Here 1 3 comes, 1 2 comes, 2 3 comes, then 3 2 also will come. 3 2 doesn't come, but when we write like in terms of I and J, see 1 2 2 3, so how many terms will write? So we take K common, and then Qi Qj upon Rij, where I and J 1 to n they move. But when we write in terms of I and J here, repetition doesn't. 2 3 comes, 3 2 3 will come, but 3 2 will not come. But here when we put Ij, there are chances that repetition 2 3 3 2 1 2 will come, 2 1 will also come in this case. So what do? We will have to make it half. Okay, all pairs, or you just write either you write all pairs, so no repetition will be there, or otherwise you just write K sigma Qi Qj by Rij. I is equal to 1 to n, J is equal to 1 to n. Okay, potential energy, where repetition will be there, so I can put half. What half will do? Half will avoid repetition, and here you write I is not equal to J. 1 1 2 2 terms will not come. This is, so basically when they ask you to find potential energy, you have to consider all the pairs. Okay, all the pairs of charge. So yeah, here also I have written it. You see, J should not be equal to K, and this half comes to avoid repetition. And then this Qj, the other one is potential at J. This is the potential at J, total potential, and then half. Okay, so now I'll take an example. When I say consider all pair, what I mean. Suppose you have a square or a rectangle. Okay, so Q1, Q2, Q3, Q4, 4 charges are there. Now when I have to find potential energy, I have to consider pair. So I'll find one pair, second pair, third pair, fourth pair, fifth pair, and sixth pair. For a cube or a rectangle, there are 6 pairs. All 6 pairs I have to consider using this formula K Q1 Q2 by R. Okay, so for these two R will be same, these two R will be same, these two R will be same. but q1, q2, q3 is different. Okay, then if you have a triangle, so in triangle there are only 3 pairs, 1, 2, 3. But if you take a polygon, suppose pentagon, okay, pentagon, then this is 1, 2, 3, 4, 5 pair, then 6, 7, then 8, 9, and then this is done 10. Okay, so 10 pairs, so you cannot leave any pair, answer will become wrong. All the pairs you have to consider.